All right, just as a reminder, if you want, I am using. I'm going off of these lecture notes right here in our module. We're doing section 1.1 and 1.2 today. Just so you know, and let's change this back to where I'm sharing the other screen on Zoom. There we go. All right. So 1.1 is on limits. Or, well, entire chapter is on limits. Chapter 1 is on limits. And you're like, what the hell is a limit? So let's say we have some function f of x. I don't know what it is, but it looks something like this. That's f of x. And we've got some point p here. And we want to find, the goal is to find the slope of the tangent line at P. Let's say this is the x naught, y naught. So a tangent line only touches at one point. Touches at one point only. That's a little bright. And that's a little dark. Actually, it's blurry too. Pardon me while I try to clean this motherfucker. How did that make it brighter? And then I didn't touch the light, that's fucking crazy. Oop. Sorry, does doing this help? Yes, it does. Okay. So. We don't really have a way of doing that yet. What we're gonna do is we're gonna start. I'll make another point over here, Q. And we'll connect these two lines. Or connect these 2 points. And when a line touches the graph. Or when the line crosses in 2 spots. It's called a secant line. And let's say like Q is x1, y1. Well, we could find the secant line. You know, y2 minus y, the slope of a line. y1 minus y0 over x1 minus x0 here. Normally we say y2 minus y1, but I labeled them 1 and 0. So we could find the slope that way, but that's not the line we're looking for, right? So what we're gonna do, the idea of in calculus is we start there and then we make. Green doesn't want to come through, let's screw it over, get the ink going. Okay, we'll deal with that later. Make Q approach P. So Q's here. Like Q1, or call Q2, Q3. If Q is like super close to it. Oh shit, thank you. If Q is super close to P. The tangent line is gonna be like, or the secant line is gonna have a slope that's almost identical to the tangent line. Does that make sense? Does it seem realistic? And so, and we make it get as close as we possibly can. If I could zoom in more and more, eventually Q is damn near right on top of P. But we've got two different points and we can make a secant line, we'll have the slope. That's the idea of what we're doing. So like, let's say, that's not the graph of this function. But let's say y equaled x cubed. And we want to define the tangent line at 1, 1. So like, and the reason why I say like this, because the line would actually be for the secant line. It's gonna be, remember doing like y minus y naught equals m times x minus x naught from algebra? That's what we're doing, but now we're using m secant here. So this would give us a tangent line, or gives us a line. So let's solve for m secant, and we had it over here. M secant is y minus y naught over x minus x naught. And x naught and y naught are both 1. We're doing it at this point here, so x naught and y naught. What's wrong? What's wrong? Doesn't ring a bell?
Oh, no, I was just wrong.
Okay. So like. We don't have any information we can do with that though, but we do know y equals x cubed. So we're gonna stick that in. X cubed minus 1 over x minus 1. See fair? And that actually factors, is the difference of cubes. That's x minus 1 over x squared plus x plus 1. The bottom is still x minus 1. So as long as x does not equal 1, we can calculate this. M secant will be, we can cancel out the x minus 1s, right? It would just be x squared plus x plus 1. Because like it's on top and bottom. But if I did like x equals 0.9999. M secant is 0.999 squared plus 0.999 plus 1. This is really close to 3. It's like 2.9 something. But just, 2.9999, it's gonna be really small. But it's really close to 3, and the more decimals I add to this, the closer it gets to 3. Does that make sense? And I can come from the other side. 1.0001. It's also gonna be approximately 3. That'll be like 3.00001, but again, the closer I get this number to actual 1, without it being 1. The smaller this gets closer to 3. And since we know, like in the original Y, we can actually plug in one. Like we could actually do the one here, even though we shouldn't, because we're doing n secant like this. I'm gonna plug in the one and we'll just show what happens, like m tangent should be exactly at one. I tried to grab my green pen again, damn it. As x approaches one, this ends up being 1² plus 1 plus 1 is 3. So we'd have our slope is 3. And we could find our line. We stick 3 in up here. We have y minus 1 equals 3 times x minus 1. From our secant line up there, and now it's our tangent line. This is the idea of limits.
I have a question. What is the word that says after the one below the tangent line, 2 words?
Here. Or here,
Yeah.
gives us a line,
I'll give us.
yeah.
Okay.
One more time, how did you get the tangent line or the tangent equation?
I'm just saying, we're gonna do plug in one because like we know the graph exists there, I could do a lot, we know what y equals x cubed looks like, right? At x equals 1 right here, the tangent line should look like this. So we know it exists. And so this approach here with having x minus 1 on bottom isn't really a deal breaker. Like in this case, this is just a scenario leading up to it. Sometimes we don't, there will be a hole there and we can't do it. But like in this case, we can actually find the tangent line by plugging in x equals 1. The approach should be the same. This is the idea of limits, getting really, really super fucking close to something, but not touching it. It's like having like a really, like the Golden Gate, you're going over the Golden Gate, and there's a fucking hole in the bridge. Like, and like the Golden, maybe the height of the Golden Gate is the function. Like f of x equals the height of the Golden Gate, so as you go closer to the hole, you're getting higher and higher and higher, let's say it's at the top of the bridge, like the very peak of the bridge. You can come up from the our side, or you can come up from San Francisco side for Golden Gate, wait, Golden Gate goes north. You can go from San Francisco over, or come from the other side into San Francisco, both ways, you're getting the same height. But you're never gonna get on that hole, because you're asking to fall through. But some people will get close and like, nope, that's fucking close enough, this is really high, I can see there's a hole. And then there's other fucking psychopaths, you're like, oh my gosh, you're gonna die one day, where they walk right up and you're like, they're looking straight down. And you're like, it's just one push, it'll take one push, I could shove your ass over. The idea of the limit is getting as close as possible without actually touching it. And does that make sense? We're gonna do a lot with that. But some people struggle with the idea of what a limit is.
Is there actually a hole in the Golden Gate Bridge?
No, I
Oh,
don't,
okay.
no, oh God, I hope not. Like, fuck, my uncle who works there, he's gonna die now. No, that was just an example.
Okay.
That's kind of like what part of what we're gonna be doing this semester. Let me know when, does anyone need this up longer? Okay,
No. Okay.
how much time you need this way?
I don't need to come back. Don't worry.
What?
I don't need you to come back with the page.
Okay. Alright, let me show you guys something. Something else I need to share on the screen so he can see it. That is annoying that it does that. So like the next part, we're looking at, we're gonna find the area between 0 and 1 for y equals 1 minus x squared. So this is like a parabola pointed down. Back, we'll take a look at it. I have it loaded right here. And calculus also gives us a way to find this area. This graph right here is y equals 1 minus x squared. And we can find the area between the graph and the x-axis if we kind of break it up into little rectangles. Now, there's a couple ways we can do the rectangles. We can do the rectangle where the graph actually touches on the left side of the rectangle like it is here. So this rectangle right here, the left side is touching the graph, the right side is not. And this is giving us 0.715 right there. Notice we got a lot of extra stuff that's not there, that shouldn't be part of the area. We can also change it so it looks like the right endpoint. How I edit this. Set C equals 0 for left. If I do the right side, now the right side of the rectangle is touching. And now we're missing some area though, right? We got some white underneath the line. But now it's like 0.615. So like somewhere in between, we can pick like the middle of the rectangle touches the graph. And so now for like here, we're missing this spot, but we have this spot. And the idea is it kind of offsets a little bit. The middle of the rectangle does a pretty good job for all of them. And notice it has 0.6675. But that's with pretty big size rectangles. What if we make the rectangles thin? Like n right here is giving us the number of rectangles. There's 10 rectangles. If I go less rectangles, like 4 rectangles, we can see what the area is looking like down here. But the more rectangles I do, the less bad space there is. See that? And I can do a lot of rectangles, and now it looks like if I do have extra or less, it's very minimal. And so the more rectangles we do to calculate this area, the better this answer is. Like I can do left endpoint and right endpoint here, and they're both getting close to 0.66. Where the one in the middle is 0.68, like this looks like it's gonna be 2/3. If I could go further, can I go further? Yeah, the more zeros I add, the more rectangles I add. This now looks like the exact area that we're looking for. And this is 2/3, that value is 2/3. But when we only had like 10. Some of these other approximations are far off. So in calculus, part of the things we're gonna be doing. Is finding areas of the curve, underneath the curve. And we're gonna make n as large as possible using limits. Okay? That's something we're headed for. That's the big picture of things we do in calculus. So the tangent line thing is called derivatives. And this area under the curve is called integrals. And that is like the heart and soul of calculus. Those are the two main functions of calculus. That's what we're doing here. Let me go back to the camera. I got the camera. Okay. Let's go back to the limit thing a little bit more. I gave you like a generic, like big hand wavy description of it. When we do limits, this is how we write limits. So we'll write it as, we use limits, we'll say LIMs for limit. And just like I showed in the other page, I said, as x approaches one. That's kind of what we do here. We'll say x approaches, but it may not be one. It could be any value. So I'm gonna say x approaches a. And we're taking the limit of some function. And assuming it exists, we're gonna say it equals L. So this is just a generic value. We don't know what it is. Depends on f of x. It's kind of like putting in a C there, but we use L for limit. And the way this is read is the limit of f of x as x approaches a is L. That's how it's read. So let's make some conjectures. Let's try to figure out. A couple limits. Let's start off with like the limit as x approaches two. Of x minus two over x squared minus four. And we're gonna do like a little table. We'll call that y. So I don't want to plug in two, but I want to plug in values close to two. So like, let's say we plug in one. I end up with -1 on top. And -3 on bottom, so this is like 1/3 or 0.333. And this is a calculator activity. I did one in my head because I can do one in my head. But I don't want to do 1.99 in my head. So I'm gonna do 1.99. Well, I know the top. And I'm gonna divide it by 1.99 squared minus 4. So I'm doing 1.99 minus 2 over 1.99 squared minus 4. And I get 0.250626. Maybe let's come from the other direction, see what it looks like. If I started at 3. 3 minus 2 over 3 squared minus 4. That's 1 over 5, 0.2. And then maybe if I try a number that's really close to 2 but above it, let's say 2.01. I'm getting 0.249376. With some change. I think I should round it somewhere there. So if I were looking at it like on a graph, I don't know what it looks like, but like here's one, here's two, here's three. We'll say that's like 0.5, 0.25. And in between there, like when X was 1, it was like right about there. When X was 1.99, it was right above 0.25. When X was 3, it was like 0.2. The Y values, right, is what I'm putting right now. And like if it had 2.01, it was right below 0.25. So it's looking like maybe if they connect right there, like that would be 0.25. These two are approaching 0.25. Does that make sense? They're really close to each other. And I think if I did more decimal places, we should get even closer and closer.
But we won't reach it, right?
We won't reach it because we can't stick in 2, right? It's gonna break this function. We'll show it on Desmos in a second. Okay? Like if we factored this though. We would have x minus 2, x plus 2. And the x minus 2's cancel, assuming we can't plug in 2. We have 1 over x plus 2. So like if I plugged in 2, I would get 1/4, and what is 1/4? 0.25. So that 0.25 seems reasonable, right? We'll look at it on Desmos in a second. I want to do another one. Let's see. Actually, let you guys try it. Let's try. Take like 2 minutes, make a little quick table for it.
I just have a question. The graph you made, that is supposed to be in a straight line, or it should be like something like wavy?
I'm just plotting points that like, this is not the graph.
Mhm.
I'm just plotting data, okay? Like, we'll
Okay.
see what the graph is in a second, just like I was trying to show, like, from the left, they're going downward, the points are going downward. From the right, the points are going upwards. It looks like coming from 2 different directions, they're approaching that 0.25. That's what I was going for. So don't fixate on whether it's a line or not. I don't know if they would, I don't know if this data makes a straight line or not, and
Okay.
since. Well, it should, but. Alright, let me give you guys one to try. Let's do limit as x approaches 0. Of sine x over x. So maybe make a little table with x and y. Maybe do -1. -0.0 or -0.5. -0.01. And then come from the other way. Start at 1, maybe go 0.05 and 0.01. Using your calculator. In fact, if someone's doing it, tell me what -1, what these values are, and I'll write them in. Well, if someone's doing, you should be doing, I asked you to do it.
0.017. How much do you want me to round up to?
Let's just do like 3 decimal places.
3 decimal? 0.017.
0.017. That was the -1, right?
Yeah.
Right. What do you guys get for -0.5?
0.009.
0.009, looks like it's going down. Did anyone else get that value? we have no confirmation on that value?
Yes, right.
Okay. What about negative 0.01?
I got point 0.000017. It has 4 zeros.
Yeah, okay. So maybe telling you to round to 3 wasn't the right idea. Huh. Feels wrong.
Are we supposed to be in a specific mode for calculator? Or is
Degrees, right?
degrees fine?
It should be radians, everything you, like generally when you trade, you use radians after you learn radians. But, those, well, they would be a lot different for degrees versus radian, no, they're not. Yeah, 1 radian and 1 degree are substantially fucking different.
Okay, so then that's gonna be wrong.
Yeah.
Cause I was in degrees. It's just-
Okay, let's, alright, let me cross those out. Let's start over, what's the negative 1?
0.841.
0.841.
841.
That sounds more right.
That's- Second one's 0.95. 9, I put running up 3.
That's good. Yeah, definitely in radians. And as we go through the calculus, you'll see why. Like the formulas that we get with degrees are fucking atrocious. Unless you like having 180 over pi and shit like that in your functions.
0.999. Well, if we round 3, it's 999, but if you keep going, it starts at 83334.
Well, 0.999 is good, we'll see what happens. What happens when we come from the other side?
Zero point 841.
For 1 or 0. What?
Oh, for 1, I did 1.
Okay, okay. Well, that's neat, negative 1 and 1 have the same value. Interesting, right? I'm wondering if these other ones are gonna have the same value too.
0.01 has the same thing. 0.999.
So I'm guessing this one's probably 959. So it looks like here's our. Here's 1, and as we come from the left. The points are rising up. And well, maybe not that low. We come from the left, it's rising up. As we come from the right, it's rising up, it looks like they're going towards 1, right? I mean, we could do more decimal places, but 0.999 and 0.999, there's not a lot of width. There's a pretty, like, if we had more decimal places, there would be a difference. But that's the kind of idea what we're doing here with limits, we're squeezing in on the value. If it does exist, if there's a limit, we can squeeze in on that value and find it. Now. On the test, you might have one problem that'll ask you to do a table. But we are going to quickly learn methods that you do are way faster than the table. And I don't want you using the table except for on like the one that says, go ahead and do the table. Okay. I'm saying that now because like the first semester I taught this last year. Someone tried to do these tables on all of the fucking calculus in like chapter 1 and 2. I'm like, no. You fucking you applied the shit from section 1.11? No. You can redo it, retake the test, do it right. And they got mad and complained in my like review. Like said I was unfair, I'm like, really? Cause I wanted you to do some calculus in a calculus class? Alright, let's take you over to Desmos and we'll take a look at these graphs. Let me, yeah,
Is one way more accurate than another? Use the table versus whatever we're gonna learn later on. Is one way more accurate than?
yeah, the other way is more accurate.
I have a question. When we have a small break so I can go to the restroom.
It's only been like a half hour, bro. But in like 10 minutes,
Oh,
okay?
Okay.
So where was I? Let's do this one here first. So on this one, what we're doing is x approaches 2. So like. We said it was 0.25, right? So I'm looking at the y value right now, because that's what we're looking for. What is the y value? So as x approaches 2, it looks like it's approaching 0.25, 0.25. In fact, if you look at the graph, it looks continuous there, right? It looks like the line is straight, right? Coming from the left or coming from the right, they're both approaching this 0.25. Notice what happens when I put. It's undefined. Okay. But. Just because it's undefined, does that not mean that's the limit? The limit is what it looks like as we're getting close to it, not what is the value when we're at it. Like, how high are we up on the Golden Gate Bridge as we get closer to the hole? Not how high up are we if we try to stand over the hole. Does that make sense? So like, if the limit here would be 0.25, even though the function is not defined at 2. And we can see that in the function. If we plug in 2, the denominator is 0, and you can't have a 0 in a denominator. So like, that's clearly a no-go. Same thing with sine x over x. We were going as x approaches 0. As x approaches 0, this denominator is 0. So it's gonna be undefined at 0. But as we were coming from the left, you guys saw you had -1 and you said 0.841. We did -0.5 and you guys. There we go, 0.959. You guys were getting these values. So as we get closer and closer, it's approaching 1. Even though the value is not 1 or at 0, okay? Let me go back to the other screen. So. The limit here is 2. Why did it get all crazy bright again? And the limit, not 2, 0.25, sorry. And the limit here was 1. Even though the functions don't exist at those values. Does that make sense? People strike, if it doesn't make sense. Come to Mesa on Saturday, like limits don't like click with some people. And so there's nothing wrong with that. But the show does have to go on. So as I was showing you guys, we did the limit. We were calculating limits from the left and the right. Approaching from the left. We call doing it when we do only one of them. They are called one-sided limits. And the notation we use. From the left. Limit as x approaches a, and we put a little minus sign to say it's approaching from the negative side. Left side. Y'all are a bunch of smart STEM majors. Guess what it looks like when we approach from the right? It's a positive. And maybe I should put the f of x equals L here thing. Finish it. All right, let's take like a. I don't know, 8-minute break, something like that, or Sway goes crazy over here on Zoom. You gotta use the bathroom or something like that. You can go to the bathroom now, Josue. Oh shit, we got 3 people.
Okay, okay, thank you.
Alright, let's continue this back up. So like this was a quick question people were asking during the break. Like, is the limit y? Is that what we're, because that's what it sounded like, and that's what it is. When we're doing the calculating limit is we're doing what is y as x gets near that value. That's what limit means in general. Well, the way we've been using it. Let me just say that now. The way we've been using it. Yeah. Okay, so these were one-sided limits. So we're gonna say a limit exists for f of x if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. And that means it's got to equal some value L. That just means it equals the limit as x approaches a of f of x, which is L. Some number. In our previous examples, 0.25 and then 1. So it has to equal the same value approaching from the left to the right. That whole bridge scenario changes a lot. If you come from the San Francisco side and you're 1,000 feet up, and you come from the other side and the bridge is only 500 feet up. There's more than a hole there, there's a fucking vertical shift of a lot, you know what I mean? So it's gotta be the same height from both directions. Yeah, I like this bridge analogy, it works.
Regardless of where it's at on what number you're using, whether it's positive or negative, it's gonna be the same spot on y.
Like,
Yeah,
Okay,
we're gonna do an example and show where limits don't exist and where limits do exist. In fact, I was drawing the graph that's underneath this. We'll look at it on Desmos in a second, just to show them all if we want, but I don't know that we need to. We can look at it and see it here. You guys ready? For those of you that printed this out. Printed out the notes, this is just some function, we'll call this f of x. It's called a piecewise function, I don't know what the equations are. I could figure it out. Well, I can figure out part of it. easily enough. The top part, when x is. Or -2 less than or equal to x. Less than 1. I don't know what that function is. That looks like it might be like a sine function. With like a really high number in the middle, like sine of 10x or some shit like that, I don't know. But I can see when x equals 1, this value is 1. And I can see when x equals. When x is greater than 1, oh, let's do this. From 1 to 3. Let's see, if I extended this rise over run. This looks like it's a rise of 2. And this would probably make it 2x minus 2 is what it's looking like to me. Let's see, if I plug in 3, do I get 4? 6 minus 2 is 4. And if I plug in 2, do I get 2? Yes, I do. So that's the line. I don't know if the top one is some sine function, but like. Find the limits, find the following limits. Or new, in fact, if it's on Desmos, I could probably easily see what that function is.
I think it's just sine half or like half a sine.
Half a sine generally makes it wider.
Not 2 sine.
Yeah, I was thinking it was higher. It's probably got a pi in it to make it so it has a nice even increment. In fact, it's doing a full oscillation in one motion. It's probably x over 2 pi. We'll look in a second. Either way, let's find the limit as x approaches 1 from the positive side. That'll be A. B, limit as x approaches 1 from the negative side. C, limit as x approaches 1. Limit as x approaches 3 from the left. And limit as x approaches 0 from the right. They need to get the pest control in here, there's a bad case of barking spiders. Alright, so x approaches 1, this is 1 right there. When we're approaching it from the right, what does it look like? Well, we're looking at this line right here, right? If we're approaching 1 from the right, like that's 1, so we need to come in from the right. It looks like, what's the y value there? 0, it looks like 0, right? Do you guys agree? What about if we approach from the left? It does some crazy shit, but as we get really close, it looks like it's approaching 2. What's the limit as x approaches 1? Does not exist. These don't equal each other. I am perfectly happy if you write DNE. But you can write does not exist or undefined, or, you know, some shit like that. Yeah.
Why does it exist?
Because these two values are not the same. This is like having a, you know, here's our Golden Gate And rather than having a hole, like this side is in ruins. Like, let's say San Francisco's sinking into the fucking ocean. And like only half the bridge remain, you could approach it from one side and yeah, you're getting to the height, but like if you try to come from the other, you're on the water. That's some dark shit. You know, San Francisco wasn't there, it was like a landfill, right? They made San Francisco. That's a man-made island. That's some deep shit right there when you think about it.
You know, we've had so many freaking earthquakes too, I feel like we're just gonna break off and become our own island.
Why would you build a fucking island on near somewhere where there's build an island somewhere when you're a fault line? It's fucking stupid. I don't get it. But it was made a long time ago and they didn't know a lot about fucking. We've gotten much better at science, let's just put it that way. Alright, what about as x approaches 3 from the left? Look like 4, right? Does the limit as x approaches 3 exist? No. Because there is no function outside on the right side of it, so. So we're gonna say limit as x approaches 3 doesn't exist. Because there is no right side. Like I deliberately put a point there and I didn't have a line going on. Right? What about limit as x approaches 0? Looks like it's coming in at 2, right? Boom, 2. And even though when x equals 0, like f of 0 equals 2, there is no limit there either. Just like here, f of 3 equaled 4. But the limit is not really what does it equal there, it's what's happening on the approach.
How do we know which one to apply the function to? Since there's the line and then there's the squiggly on the left, how do we know which one the function's gonna apply to?
So it's what value you're approaching. So like when we're approaching 1, we're here. So if we wanna come from the left or from the right, that's from the right. And if we wanna come from the left, it's following this path right here. Does that make sense? Now I wanna know what that function is. I don't think I need to bring it up, because everyone seemed okay with that. That was sine 2 pi x. Plus 2.
Wait, so how does limit x approaches 3 from the left side, how does that equal 4?
Because that's what it's approaching. So we can have values for the plus or minus approach. As long as those things there, but the actual limit at the spot. One-sided limits. This, okay, this, and this, the red ones are one-sided limits. They can have values. The two-sided limits. Only have values. If it's the same from left and right. Does that make sense? It's a little nuance there, but it's a distinction. And it's because of these piecewise functions. And they do exist in real life, it wasn't just like this one, I don't know what this one would be for. But there are plenty of examples in the real world where piecewise functions are actually modeling something. You guys ready for a little bit more on this chapter, or this section? You have a question?
No.
You sure? Okay. Does anyone need this up longer? I don't read mine, so if you don't say something, you're losing it. Alright. So infinite limits. Like things like limit as x approaches a from the left of f of x equals positive infinity. And limit as x approaches a from the right equals positive infinity. This is kind of like saying, the closer we get to a. The function increases without a boundary. They usually just say without a bound. And just like. Sky is like a boundary for us, this is almost like limit. Without a limit. So it keeps going up indefinitely, we will say, even though infinity is not a natural number. We will say that the limit. As x approaches a of f of x equals infinity. That's what we're gonna say.
Is the positive from the infinity necessary, or can we just write infinity?
I was writing positive because like, it's not necessary here. I was just making it clear because. Like, what's going on? How would we get one? How would we get? Limit as x approaches a of f of x to equal negative infinity? What has to be going on? Think about that for a little bit. No, not a straight line, definitely not a straight line. One way to think about it, like maybe draw a picture of what's going on here with the top part. Don't make sense, where'd they go? There they are. So maybe I have a right here. So what does as x approaches a from the left going to infinity mean?
Increasing.
It means it's increasing, it means as I get close, I don't know what's going on ways away from it, but it's doing some shit like that. Does that make sense? So what's happening from the right? Well, it's gotta be going positive infinity as well. So it's almost like x equals a is an asymptote. In fact, that is the graph of x, f of x equals 1 over x minus a squared. And I can put in whatever value of a I wanted, and it just changes where that spike is. That infinite spike.
Okay, so with negative infinity, then that gives feet pointing downwards, right?
So negative, yeah, so negative infinity's gotta be doing some shit like that. And it's gotta do it from both sides. So maybe if we did negative 1 over x squared. Here a equals 0. It's gonna point downward on both, and we would get negative infinity as a limit. Now, I do have another example in the notes, but it's just making a table. And I made you guys do that table earlier, where I normally don't. And I think people got the table. Cause you really don't need the table after the next section.
Where did the A equal 0 come from?
I just,
It gave it-
for this graph, A would be 0. Because this is negative 1/x minus a squared. The squared makes them point in the same direction. The negative says this is that, because x minus something squared is always a positive number, right? So in general, this thing's always positive, and if I slap a negative on it, it's always negative. And I just chose 0 because I actually put the y, like I drew an axis on there rather than an asymptote. And I thought, fuck, I already picked a value there for a, so maybe I need to write it down. But we could have it shift somewhere else. Like A's over here and do some shit like this.
I see what you mean.
Alright, does anyone need this up longer? We're gonna start 1.2. You know what, I'll stop this video. And we'll have 2 videos. That way they're separated for you.